Welcome, everyone. My name is Nicholas Lane, and you are watching Flower Monthly for June. We have a pretty fantastic lineup of content for you this month. Let me get right to the agenda for Flower Monthly June. As you see here, we have three guests. Um, the three guests here are each going to be speaking to you about some pretty interesting innovations in the world of federated learning and Flower. We're going to start off with Robert Steiner. He works at Flower Labs and has been busy building a lot of amazing things that a lot of you have been using in various parts of your projects. And so this month, Robert is going to be giving us the Flower update. And the surprise is that we're going to be talking about how we have radically enhanced the support of Docker within Flower. And so everything he's talking about is available in Nightly right now, and it'll be moved into Flower 1.9 shortly. But so everything you can see he'll be talking about is available right now for use in Flower Nightly. And so after Robert is given this Flower update, we're going to move on into the other two guests that you see here with me. First, we have Madi. Madi works at Huawei Canada. He is going to speak to us about one of the sort of the big topics, the big looming topics in machine learning today, that being foundation models. And he'll be telling us about some pretty interesting technical work they've been doing to use foundation models and federated learning. And so we're going to hear from him as our first invited speaker. And then we'll close off Flower Monthly for this June month with Sergio. He is going to be talking to us about a really important and cool project called Green. Some of you would have seen his poster at the Flower AI Summit a little while ago. And then we got quite a bit of reaction to what he was talking about. And we thought it would be great to have him back to talk about this in an extended fashion. So that is what we've got for you today. Let's move to our first speaker. And so, as I mentioned, our first speaker is going to be Robert. He is going to talk to us all about the sort of the big enhancements for Docker support in Flower that's now available. So over to Robert.
Thanks, Nick. Welcome, everyone. Today, we want to share some exciting updates we have made to our Docker images. So let's start with our new images. So with the next Flower version 1.9, we will release the first version of our new Docker images, Superlink, Supernode, and Server App. That's a big step because the new images enable everyone to deploy Flower end-to-end in Docker in a production environment. With the upcoming release, we will also deprecating our current server and client images. The server image becomes the Superlink and the client becomes the Supernode. You can already migrate to the Superlink image today. We released a 1.8 Superlink image that is identical to the 1.8 server image. The client image is a bit different because it was never publicly announced, but if you have used it, make sure to switch to the Supernode image after the next Flower release. If you have any problems, then just reach out to us on Slack, GitHub, or Flower Discuss. We plan to release Flower 1.9 within the next 2 weeks, but you can already try out our new images by checking out the Nightly images. The Nightly image contain the latest Flower Nightly, and they are available for all 3 images. But please keep in mind that Flower Nightly is not considered stable, so please don't use it in production. In addition to Ubuntu, we will also release Alpine images. Alpine describes itself as lightweight and security-oriented. Compared to other base images, it's smaller and has less security vulnerabilities, which makes it perfect for production environments. I will also show later some numbers. We also reworked our current Ubuntu image to make it more secure and smaller. We are now using multi-stage builds where we first compile the Python and then remove the Python binary to a fresh Ubuntu base. And the advantage here is that all the dependencies that are required for compiling Python are not part of the final image anymore. We also removed pyenv from the image. We still use it for compiling Python, but it's not part of the final image. And last but important, all the new images will run by default with a non-root user. You can still run the container with a root user if you want to, during development, for example, but we highly recommend to use a non-root user when running in a production environment. Going to the next slide, we can see the comparison of the Superlinked image and all so the comparisons in size for all images for the Superlinked image. So we have on the first bar, we have the old Ubuntu image, which is roughly 400 megabyte in size. Next to it, we have the new Ubuntu image. It's 200 or roughly 200 megabytes. So we almost halved the size here, which is a huge improvement. The Alpine AMD 64 is even better. That's only 64. And the Alpine ARM64 is unfortunately a bit bigger because the binary for the gRPC library is a lot larger. And it's also noticeably slower to build because gRPC.io doesn't provide pre-built binaries for Alpine ARM64, so we have to compile it from source. On the next slide, we can see the enormous progress in reducing vulnerabilities. So on the first row, we can see the old Ubuntu image, which had a lot of vulnerabilities. The main cause was the dependencies that we installed for compiling Python. They are not anymore part in the new images. What you can see here for Ubuntu New and Alpine, the medium and low vulnerabilities, that is nothing that we have introduced. They are also part of the Ubuntu and Alpine base image. And if I'm not mistaken, they all are not fixable. For the high vulnerabilities for Alpine and Ubuntu New, one of them is pip. It's also not fixable. And the other one in Ubuntu is setup tools, although that's a false positive because in one layer we install that specific version that is vulnerable to or has a security issue. But in a later layer, we actually install a newer version, but it's still flagged as a security vulnerability. But that's not part of the final image then. On the next slide, we can see the images that we will support. So for the Superlink, we will use the so if we use a base image with Python 3.11 and Ubuntu. We will also use a Python 3.11 and Alpine image. And for nightly, we will always use Python 3.11 and Ubuntu. We will upgrade to a newer Python version when we also upgrade the support in Flower. So for the Superlink, you can expect this will be always the latest Python version that we support in Flower. For Supernode and Server App, we will support all the versions that we also support in Python. So from 3 to 3.8 through 3.11. They are all based on the Ubuntu image. And we will also have a nightly image, and there we use Python 3.11. So you might wonder why we only offer Alpine for the Superlink image. And the reason for that is on the next slide that Alpine and machine learning frameworks currently don't work really well together. So Alpine internally uses musl instead of glibc, and most ML frameworks don't provide pre-built binaries for this combination. So what we often end up is that in the container, we will need to install all the dependencies like GCC and CMake and so on to compile these frameworks from source within the container, and that often results in bigger image size and also a bigger text surface because we have all the additional dependencies. So that's the reason why we decided against having append images for the Supernode and server app for now. Maybe we will also add this later. All right, yeah, I think that's for me today. You can check out our new images. You can check out the nightly images. I just want to mention that it's the first version that we release. So we will continue to improve our images in terms of security, make them smaller, and also in the experience to make it easier to work with them. And if you have any questions, ideas, feedback, then please reach out to us on Slack, GitHub, or Flower Discuss.
Great. Well, thank you so much. That was really interesting to see what's happened with Docker support in Flower. And I know this is a reaction to a lot of user questions and interest in being able to do this in various types of, in particular, production settings. So it's great. For those of you who are sort of with us live, feel free to post your questions if there are any in the Slack channel that we have for Flower Monthly, or we keep things pretty casual here. So feel free to raise your hand now if you want to ask a question, and I'll unmute you and you can just ask Robert directly. I see we have a question here in the Q&A. Let me just pop this open here. And the question is, where can I find an example of how to use the Docker images? And does the documentation have a complete example?
Yeah, so you can visit our Flower docs, which is the second link, and there you can also find an example. We also have one example that we will use for end-to-end tests. It's a Docker Compose, and that's also available in our repository. And I think I have to look this up, but you can find a Docker Compose file that also uses those images and show a whole example.
Thank you, Robert. This is really awesome stuff.
Thank you.
Great. So the next talk, the next update we'll be seeing in this Flower Monthly is by Madi Beitolani. I'm sorry if I didn't quite get it.
It's perfect. No worries.
Oh, great. Okay, thanks. And you're probably being very generous, so I do appreciate that too. So Madi, he works at Huawei Canada. And so Huawei obviously is one of these leading big tech firms that are global, doing fantastic stuff ranging from big servers all the way down to really cool phones. But they also do sort of really seminal pieces of ML research. And so he's at one of these institutions there where he is a machine learning research engineer. I also saw that he received a Master's of Science from Queen's University, along with other degrees from other institutions too. And so Madi, he works in various domains, including distributed training, federated learning, and parameter efficient fine tuning. And so interestingly, this work kind of brings a lot of those things all together. And so, yeah, I'm fascinated to see what he's been working on and how Flower has enabled an interesting piece of work to be possible. So, so over to you.
Absolutely. Thank you so much for the introduction, Nick. Thank you guys for having me. Let me just start my share my screen. Perfect. Let's go here. And yeah, can you guys see my screen?
Yes, looks perfect.
Awesome. Thank you so much for the introduction. Thanks for having me here. Hello, everyone. My name is Madi Beitolahi. I'm a research associate here in Huawei, Canada. And today I'm going to present our work named Parametric Feature Transfer, One-Shot Predictive Learning with Foundation Models. This is a work done at Huawei, and it was a joint work with my fabulous colleagues that I list here at NOAA's lab here in Montreal, Canada. Today I'm going to be an informal discussion on, let's say, federated learning and foundation models and this area around it. And I just want to point out new ideas and direction in that regard. Let me just start my timer. Awesome. So yeah, let's start. Before I start, I have to make an important disclaimer that the work is done. What I want to say and my opinions are expressed do not reflect the organization that I'm affiliated with, and these are just my opinions. So yeah, with that, let's start. So this is the outline for today. First, I'm gonna start with an introduction on federated learning foundation models, and then we're gonna talk about FedPFT, parametric feature transfer at work, and then we're gonna discuss some results, and I'm gonna show you how you can use FedPFT today in using Flower baselines. Awesome. So let's start with the introduction. So like I'm pretty sure that everyone's like watching this is you know that we are in the era of foundation models, right? Models like GPT-3, Llama, Clip, use them every day. We hear about them all the news, right? And the thing that what is important about them is that these models have huge sizes and they incorporate pre-trained knowledge, right? They've been trained on like internet scale data and they have exceptional performance on downstream tasks. But the important part is that we have to keep in mind that these foundation models should be fine-tuned on downstream tasks to be useful. Let's say for instruction tuning or any classification tasks. And that's where federated learning comes in, like federated learning for foundation models. And in order for us to fine-tune these models for downstream tasks, we have to, like some of the data that we want to use for downstream fine-tuning are our user data, and for protecting this privacy, we can utilize federated learning to also leverage the capability of foundation models. So that's where federated learning comes from in order for us to fine-tune these large foundation models. But the thing is that there are a lot of challenges when we we utilize federated learning for foundation models. As you probably aware, like traditional FL takes place iteratively over multiple rounds, right? So each client has to send the model to the coordinator after it trains, and then you have to send it to the coordinator and send it back, right? So this multiple iteration and this training and transmitting causes a lot of GPU memory requirements and communication costs. And we're talking about these large foundation models, right? So one approach that I really bring on here and I'm a very advocate of is one-shot federated learning. One-shot federated learning is an approach to address high communication costs of FL by requiring a single communication round. What that means is that my clients only send the model once to the coordinator and they just receive the updated final global model, right? And like I'm a really big advocate of one-shot FL because not only it solves all of our high communication costs, but also it has very important advantages. One is, for example, easier coordination. Everybody who's works on FL knows that how hard it is to maintain this kind of connection between clients and the server. And that's where like tools like Flower comes in and they're very good at. It just allows us to coordinate much more easily. And that's where one-shot federated learning solve this problem, right? It's just a one-time connection and it is much more easier to coordinate. Another thing is that it supports scenarios where multi-round FL is impractical. So let's say in dynamic environments that our data and user behavior is rapidly changing, we want to fast and rapid federated learning process that give us a final model instead of like running these models for days and thousands of rounds. So, and I think it's a very interesting direction that is basically a combination of model merging and federated learning. So it brings federated learning to a new paradigm. But the thing is that one-shot FL is great, but the current methods lack the performance of the multi-round FL counterparts. And we don't have theoretical guarantees because in multi-round FL, we are using the fact that, hey, we run it for a long period of times and in the end, it's going to converge. So this is very extremely challenging on one-shot FL. And also, one-shot FL doesn't mitigate the GPU memory demands, right? We still have to fine-tune these foundation models on user devices, right? So I talked about like, hey, we need to fine-tune this foundation model, but the thing is that we can also at the same time leverage them, right? Because the pre-trained nature of these foundation models, opens up new possibilities for training-free and communication-efficient knowledge sharing among clients in federated learning. And we can leverage the smart features of these foundation models as they are without excessive fine-tuning. So the whole summary is that we need to fine-tune these foundation models, but not so much, because they already have pre-existing knowledge in them. We can utilize for much more to have a better communication efficiency in the network. So what was our goal in this paper and this project? We wanted a FL method that is practical for pre-trained foundation models. So that's for our goal. The second, we wanted to make it one shot, much more easier coordination. We wanted to make it communication efficient. We wanted to solve the GPU memory demands. And most importantly, that's why we are in FL, we want to make it privacy preservable. So that's where comes in our methods. So in this work, we propose FedPFT, Federated Learning with Parametric Feature Transfer. It's a training-free one-shot FL models that enable foundation models in federated learning. So in this figure, I'm just going to show you the high level. Again, this video is going to go down and show what you're doing. So on the left side, you can see some clients are doing some feature extraction, etc. They're sending some information to a server, and server processes that. So this is a one-shot method, and now I'm going to dive in deep to showcase what I mean by that. So at each client, let's just consider client one, we pass the data set and we extract the features from the foundation model. So this feature extractor is a frozen feature and foundation models that we are extracting the real features from it, right? So we are going to pass the data set for each label. We're going to extract the features of each label of each client to get the real features. And from that, we're going to learn a parametric model. Parametric models are probability distributions that we can learn from any features. So for example, in here, we're using the Gaussian mixture model, mixture of Gaussians, to learn the probability distribution of our real features. Now, we can explain this whole label of this data set towards this probability distribution with its parameters. So in here, we're going to do the same thing for every client, and we're going to send the parameters of this probability distribution here, which are mu, pi, and sigma, which represents the mean, mixture rates, and the covariance of this probability distribution to the server. Now, the server has the probability distribution, and you can utilize that to sample to create synthetic features, right? And from all those clients can combine these synthetic features to train a classifier head. So what we're basically doing is that we're extracting the label of each client and learning a parametric model from them. We're sending it to the server, and by recreating the synthetic features, we can train the classifier head. So what that means is that after that, a user can utilize this classifier head along with the already pre-trained feature extractor to utilize it for its data set. So in here, we're focusing on learning the classifier head using frozen pre-trained feature extractors. So what I talked about here was for the centralized scenario where we have a server. But what about this decentralized case where we don't have a centralized server? So in that case, each client is responsible for aggregating and passing the knowledge, right? So this setup of GMMs can be also applied in that scenario, where let's say with each client, right, we already have our real features. Whenever we are getting a distribution from another client, let's call it a received GMM, we can just combine the synthetic features and real features and learn a new updated local GMM. So what I'm presenting here is the idea of like passing this GMMs and passing this parametric models in the network, right? And we aggregate the knowledge from the entire network. So I talked about Gaussian mixture. Now let's a little bit dive in a little bit what I mean by that. So we can use any parametric models, but in here we're using Gaussian mixture models or GMM as our parametric model. The reason we're using GMM is that GMMs are a universal approximate of densities, right? If you have enough mixtures, you can just describe any probability function, which was very cool about them. And the fact that they are very easy to estimate and work with and much more understandable was a perfect fit for us. So there won't be any math today, just very small ones. I show you why it's important to show here. So we can represent the each density function of a GMM by a set of tuples, right? So these are the parameters that we are passing to the network, right? Where I've talked about this pi is our mixture base, mu is our mean of Gaussians, sigma here represent the covariance, and k represents the number of mixtures. So the cool thing about this, if you think about it, we have two kind of flexibility in terms of number of mixtures and also how we represent this covariance matrix. It can be a full covariance matrix, diagonal, or spherical. Why that matters is that we are in federated learning and communication cost matters to us. So we want to be able to have flexibility in terms of how much communication we send. And therefore, like full covariance is has much more communication cost than, let's say, diagonal or spherical. Last thing before we get to the results is that we care about privacy. And like the thing is that we saw in papers, like they assume that, okay, since we are in the federated learning, everything is private, which is not. We have to have formal privacy guarantees in order to assure privacy. So in this, we're gonna use differential privacy. So and it's very straightforward. In differential privacy, you either add a Gaussian noise or another function. I think here we're just adding Gaussian noise to our new and signal. So this way of adding noise, we make sure that these tuples that we're sending, these GMMs that we are passing to the network, are differential private. And this assures that we are in this formal definition of differential privacy. Okay, now we're ready to show the cool parts experiments. So for our experiments, we're going to use 8 data sets and 3 foundation models. We're going to compare both centralized and decentralized topology. And for our experiments in here that I'm going to show you today, we're going to only train the classifier ahead of foundation models. But for other experiments that we fine-tune the rest of the models, I refer you to that paper. So this is the summary of all the data sets and foundation models we use. We use both ResNet, VIT-based, and CLIP. In here, we're just focusing on vision models for classification tasks specifically. Okay, so now let's to the first setup of our centralized federated learning. So this is a classical setup of 50 clients. We are using Caltech 101 dataset, and we are using CLIP as our pre-trained foundation model. So this black line here shows the federated averaging before that. So x-axis represents our communication cost in terms of megabytes, and our y-axis is accuracy, right? So this line here represents federated average. The reason this is a line is because this is a multi-iteration process, right? So we can have multiple points doing this as we perform multiple rounds. As you can see that like federated averaging starts very slow because naive averaging, right, in the first shot, first iteration doesn't perform well. But as it goes up, it reached the performance of centralized. Centralized is our oracle, where we assume we have all the real features at the server, right? At the same time, you can see that FedPFD, our method, and DP-FedPFD is very, very competitive with centralized, right? And even the DP version as well. We're going to talk about why is that. But you can see that like FedPFD is close to the centralized performance. But you can see that other one-shot methods do not work as well, right? Because how hard it is in this scenario. In here, I just have a couple of, like I just showed you here the federated averaging and 3 one-shot methods. But in the next slide, I'm going to show you additional benchmarks that we did with the same method. So in here, I'm adding more lines here. So these lines are for different multi-iteration federated methods like FedYoki, FedProx, and we're adding more one-shot methods. But the idea is the same, right? One-shot methods, current one-shot methods, without sharing this knowledge, do not perform as well as methods that utilize this pre-trained knowledge of foundation models. And at the same time, you can see like we're showing different kind of, let's say, choices that we had for the parametric models. For example, you can see having one mixture has less accuracy than having 10 mixtures, or like using diagonal covariance matrix is better than spherical at the cost of communication cost. So in here, we're just showing the trade-off, but the idea is the same. This is the next experiment, which I think this is my favorite experiment, is in the linear topology, right? In linear topology, we have, let's say, 5 clients connecting in a linear manner, right? And in this one-shot setting, right, we have to transfer knowledge from client 1 to 2, client 2 to 3, 3 to 4, and 4 to 5. And there is only a one-way communication between them, right? And using the GMMs, we can do that actually. And this is the results for that. So you can see, for example, as we pass these GMMs to each client, right, we are accumulating knowledge towards this linear topology. And in the end, we're going to reach the centralized performance as if we have all the clients' data in one place. And this is a very, very cool experiment, and it shows the capability of these GMMs as just like transfer of knowledge in a ad hoc situation. As they go past the clients and accumulate knowledge of each client. Last 2 slides is basically a discussion and analysis like on what is happening, why GMMs are working, and why is it actually private or not. So the first question is that how well do GMMs model feature distributions? So in order to figure out like how well they model feature distribution, we measure the accuracy gap between 2 classifier heads, one trained on real features and 2 trained on synthetic features of GMMs. So this figure shows the accuracy of different types of GMMs, and x-axis represent the number of parameters we need to transfer these GMMs. Interestingly, we find that as you add more mixtures, you're going to have better representation of the real features, right? And we're going to see a trade-off between number of parameters and the effectiveness of GMMs. And we showed that, hey, full GMMs are not communication efficient, but diagonal and spherical GMMs with 10 to 50 give us a very competitive edge towards raw features. And it shows that, yes, features extracted from the pre-trained foundation models does resemble a Gaussian, but not a perfect Gaussian. Last thing, which I think is a very cool experiment we did, was that we did a reconstruction attack on our federated language setup. So one way, if you think about it, is that we can just, instead of training these parametric models, training this GMM, we can just send the raw features, right? The reason we cannot do that is because of this. A user can reconstruct exact images, right, from the raw features, as you can see here. So these are 3 examples we're showing here. And when we are sending raw features from clients to the server, with other assumption, of course, an attacker can reconstruct exact images. But if we do the same attack on FedPFT or DP-FedPFT, you can see that the resulting images are not similar to our test images, right? And that is a very, very, very good news for us. That, hey, without having this DP mechanism, right, still just understanding this parametric models can protect our privacy. Okay, now just a conclusion and discussion. We're gonna have a discussion on feature works here. So in today's presentation, I presented FedPFT, a one-shot communication FL method that enables foundation models. Our work highlights the capability of private feature sharing methods for knowledge transfer with foundation models. We just wanted to show that, hey, we can utilize this pre-trained knowledge of foundation models in a private manner. And the third question, that this is something that I'm actively trying to figure out, is that how we can utilize this private feature sharing for LLMs. The result we talked about today were mostly focused on vision models, right? And that would be cool to understand how we can use it for LLMs. Okay, now, so right now you can use FedPFT in Flower baselines with just 2 lines of code. I provide the link here. And yeah, I had an amazing time creating this baseline with the with the flower, and it was the most developer-friendly experience I ever had, and I learned so much from it. And I definitely recommend not only for beginners in flower, federated learning, but also like for developers who want to start working on open source projects. I think this is a very cool platform. And yeah, I encourage other researchers to also put their baselines there so we can have formal a comparison between these baselines. And yeah, thank you so much for having me. If you have any questions, yeah, happy to
That was
answer.
great. Yeah, thank you so much. So if anyone has questions who is with us live right now, feel free. You can raise your hand in the Zoom thing, or ask a question in the Q&A thing of the Zoom. Or we do have the Flower Slack channel. So I'll take a look and see what questions I can see. I don't see any in the Zoom, but I see some in the Slack. I see there's a question saying, could you elaborate on the cases where this approach doesn't work? So you mentioned, I guess they're talking about at the end, you mentioned LLMs, and you've mainly, I guess from this question, you can imagine it's so they sort with images. Did you run into some other cases? Maybe, and are
Yeah,
they data dependent? Are they architecture dependent? Any commentary on
yeah,
that?
absolutely. Yeah, that's a great question. So one thing we notice is that like we are focusing here on the last layer of before the classification layer. And the thing is that we cannot do this for any layer of a network because before the that's the one of the main like limitation of this work is that we can just use it for classifier head because other layers have like there's a positional embeddings in them that we cannot just use a simple Gaussian. So this last layer before the classification, because the way these foundation models were trained on, made it possible for us. Basically, they were separable. These labels were separable, so we can just learn a Gaussian. And one of the main limitation. And the second thing, as I pointed out, was the LLMs. Like like this kind of area of like this image classification is much more straightforward than translating the understanding the last layer of like a next word token prediction, right? Because we not only we have embeddings there, we have to figure out, but also like we cannot just learn a Gaussian for each label, right? So it doesn't translate very well to that setting. And this is something that I'm want to work on that to see how we can bring the same idea of like this knowledge of pre-trained models to send them more efficiently in Flower, in federated learning.
I see. Okay, cool. Interesting.
Yeah.
Very cool. Let's see. Oh, there's another question here. What's the intuitive explanation for why FedPFT is more secure? Is it primarily because of the low rank nature of the model representations being shared, or is there something in FedPFT actively preserving privacy?
Yeah, that is another absolutely fantastic question. Yes. So the thing is that FedPFT, like any federated learning, including FedPFT, with itself does not have a formal privacy guarantee. That's why we went to DP FedPFT to have a formal privacy guarantee. But as you saw in the end, like that was surprising to us as well that it was private for this specific construction attack. Like we have to be very specific in terms of privacy that like we haven't like nothing is private until like you cannot prove privacy towards attacking because there may be another attack that like FedPFT is not private on, right? But the reason that we saw that hey in here was private was absolutely you're right. If this low rank nature, this encoding of towards this Gaussian mixture and resampling right from these mixtures allowed us allows the server to not be able to exactly resample the features from the sender. So we are just encoding it to a very lower dimensional, low rank space that allows us to have this kind of cool behavior, not being able to reconstruct the exact features.
I see. Yeah, makes sense. Cool. I actually I had one basic question, which was in one of the slides, maybe a slide 20, you showed the DP version of this and the standard version of this. Hey, this one. They're quite close in accuracy. Or actually, on second look, maybe it's a decent gap. It's like 10% gap there. I was just wondering, DP is quite tunable. And so could you speak a little bit about how did you tune this DP where there's a bit of an accuracy gap? Is it, for example, the same tuning for which you later show these example images? Is it the same kind of intensity and settings of the DP, or is it different?
Yeah, for sure. Like the thing is that like we treat Fed PFD and DP Fed PFD are exactly the same. Like before we send it to the clients, the only difference is that in here after calculating the covariance, mixture weight and mu, right? We add the noise. So before that is the same. For I think I don't remember exactly the delta and the epsilon we used, but we just set to fix the delta and we tested for different epsilons and we just reported the results. And yes, like the gap actually is kind of far, but it's way better than we expected. The reason was that this Gaussians, right? It turns out that we don't need to add too much. That's one of the things that I love about one-shot FL, right? In the multi-iteration FL, because you're processing data again, doing the training, right? You have to have a lot of privacy budget, right? But because we're in this one-shot setting, we just process the data once and we calculate the means. So that is why we're seeing a better utility trade-off for us because we just process the data once and we add the noise. Unlike like federated learning in iteration that we have to add noise every time.
I see. That makes sense. Okay, cool. So one last quick question, and then the question is, which decentralized network topologies have you used this work in? And is it only that linear topology you showed us, or there are other ones? Or can you speak
Yeah.
a bit about that?
Yeah, for sure. We tested multiple scenarios. I just showed here the linear topology because I thought that was the coolest one. The other ones that we did was based on two clients, peer-to-peer connections. Let's say we have user A, user B, and user A can only transmit once to user B. And actually, in there we tried different types of heterogeneity in terms of label shift, covariance shift, and path shift. So you can think of like user A has, let's say, images of a car, and user B has images of foods, right? And it was a very pretty cool experiment, and we saw the same results. But that's absolutely a great point. This is something in the future we're gonna consider, like let's say, a more decentralized topology, and have to read like what are the main benchmarks they're using for decentralized learning, and we're gonna compare on that regard as well, for sure. Thank you for the question.
Okay, awesome. Well, thank you so much. We're sort of a bit out of time for this segment, so I see another question, but I'm afraid we'll have to take it offline. So please post your questions just in you can mail them to me or post them in the Slack, and I'll forward them along to Madi. So again, thank you so much for the talk. Great stuff. Really interesting use of federated learning, and it shows how it can really be a powerful tool for us to build models of this kind and leverage the other tools that are around, such as these foundation models. So very, very nice.
Thank you, my pleasure.
Great. Well, then let me transition. To do that, I will show you this slide. And so let me introduce Sergio Zaera Mata. He works at HI Iberia. And so this is a Spanish-based organization that I believe develops technology for people to use machine learning methods and so on, and now allowing them to build it into their business and so forth. He is an AI engineer. And then as I mentioned earlier, he was at the Flower AI Summit a few months ago. He is a really interesting piece of work. And so we thought it would be great to have him back and to kind of give us an extended sort of deep dive into this fantastic project that's called Green. where he's using federated and collaborative sort of methods for learning with the aim towards helping us build and maintain more sustainable cities. So it's really an important application domain of this stuff. So thank you for joining us, and over to you. We're really fascinated to hear about your work.
Okay, thank you so much, Nick. Let me share the screen. So yeah, thank you so much for having me here. Today I'm going to be presenting Green. Yeah, I'm Sergio Zaera Mata. I'm an AI engineer at HI Iberia. And yeah, Green is it's called also Collaborative Intelligence for Sustainable Cities. And yeah, let's go. So first, I want to present a little bit of the company, just to let you know. At Iberia, it's an innovative SME. The main objective is to develop artificial intelligence software for the industry and also for the people. And now we have more than 120 professionals, where 90% of them are engineers. So we are allowing the company to have high level of innovation and interest in the new technologies. We specialize in different kind of sectors. Here you can see some, the space, also Navy, energy. Here the Project Green, which is smart cities. We have different kinds of projects. So yeah, starting with the presentation, let me give you just the index and so you can navigate through the teams. First, the introduction, and then I'm going to explain what the solution that we're preparing, show you the digital twin that we have is the virtual representation of the city, also the models and data that we use, the results that we have, why it's important this technology combination, and that is the kind of the very important part, and finally applicability and conclusions. So yeah, starting with the introduction, Green, it's also called in Spanish Inteligencia Colaborativa para Ciudades Sostenibles. It's close to the thematic of the smart cities, and the use case of Green was to managed to get the energy demand prediction of a model for the charging station and the charging environment of the electric vehicles. The project starts with, or starts thanks to the company red.es, which is a public corporate entity that is under the Ministry of the Transformation, Digital Transformation of Spain, and specifically to the artificial intelligence part, which is we are doing. Also, the mission of the company is to execute programs and accelerate the digitalization of Spain. In this project, we are collaborating with Naturgy. Many of you can hear about this. Naturgy is a multinational company from the energy sector and has the headquarters in Spain. And it's dedicated to the generation and distribution of and commercialization of energy and also natural gas. So yeah, we are collaborating in, of course, because in our company we always look to having all the projects and expert in the domain, so we can help each other. And basically, the objective of the Green, the fundamental objective was to create a AI platform, obviously in the industrial level, and to enable the implementation of this project, but also other projects in the future exploiting this IoT data. So before continuing, I want to make a quick explanation of the charging environment, just to know the main concepts. So first we have the network provider, that is the company that transports the electrical energy and builds and maintains the transmission facilities. Also we have the charging stations, that is the infrastructure that links obviously the energy distribution with the charging of the electric vehicles. Then each charging station will have a charging station manager, that is the electricity consumer authorized for the supply of this energy. And also, finally, in the last part of the ecosystem, we have the electric vehicle users, that are the users of the electric vehicles that need this energy to run. So the use case of Green is to create a prediction model for the energy demand that is required for the charging stations, and the real part is to optimize all this environment that I already present. Here you have representation of it, where all the parts of the environment help each other just by adjusting or by predicting this energy demand. So helping one part will be helping and optimizing all the environment. Okay, so for just trying to doing an introduction, I want to explain like the functional schematic, which is the combination of the blockchain, the federated learning, and the smart contracts in this technology scheme. So first we will have the IoT devices that in our case will be the charging stations and the sensors there. That connects and use the data of these charging sessions to update the local models in each charging station. Then these local models will be added and well, first validated and then added to create a global model. And finally, we have all the process to update this global model to the rest of the charging station that have participated. Don't worry, I will explain this better, but just to a quick overview. So the solution. Why we need a solution or why we start making a solution? So we identify three challenges. This challenge was not only for the energy and the mobility sector, but also are across all the industry and the sector. So first, the security. It's important to secure the relevant and the sensible information to avoid not only internal threats but also external threats. Also, reliability. The companies are sometimes not willing to collaborate with each other and to share data because that will mean to lose these benefits of competing. But that is starting to be a problem. In the future will be really more, and we need to see what we do about that. And finally, the decentralization. Well, the real problem is the centralization because decentralization of the service and the process, there are really big problems and they can obstruct, let's say, the agility to the companies to adapt to the changes. So we start to need to decentralize the systems. So yeah, for the to this challenge, we wanted to solve them, and so we arrived to the project Green. Here you can see a quick view of the Green network. As I told before, we have a combination of the three technologies, federated learning, blockchain, and smart contracts, and how these technologies interconnected. So first, we have a federated learning architecture, so that allows the different users to collaborate with the local models in the creation of these global models. But we didn't want to have a central authority and a central server and to share all these local models. We wanted to be this sharing and validation process in a decentralized environment. And that's why we introduced the blockchain network. This blockchain network is offered as a service. So the people will be private, but the people that are allowed will be able to connect and to participate in this network. And obviously, this network needs to be regulated. And to be regulated, we need to establish some immutable and transparent rules that are called in the blockchain environment the smart contracts. So we are not building just a solution, we're building a transformation in the sector, mixing these technologies. Okay, so here you can see a big picture of the architecture of Green and the different models. First, we have the simulation model. That is the one that we use to create the digital twin. We implemented that with using the SUMO. It's called the simulator of urban mobility. Also, after you have the data collection model that it's joined with the ML model. When we use some models of PyTorch and most of them from NVIDIA. These IoT devices, this join of the two models are connected first with the blockchain model. That is the one that has the decentralized network and allows this interaction. And the blockchain model was done using Hyperledger Fabric. And finally, we have the federated learning model, which is obviously done by Flower, because we spent really long time deciding these kind of technologies, and Flower was the one that really like a small, best documented, and really it's really great. So yeah, in the energy demand prediction, I told you before that I'm going to explain in detail how this process is done. So for the ones that didn't understand me before, here you can see more clearly. So first we have the data collection, where a car goes to the charging station and charges the battery. So this data is collected from the charging station to the energy demand data, and its model, its training with its local model in its training station is training with this data. Then this model is shared with the rest of the charging station is the net. So the model can be evaluated by each of the charging stations. So one of the models can be approved, but the other no. So we have a voting process where the model in this blockchain network is shared, the weights of the model and also the metrics. So another charging station with kind of the same situation can evaluate if the model is good or not, let's say, for joining the net. Because if the metrics that obviously with some percentage of error is inside this rank, can be up to enter in the net, but if you detect that it's an anomaly, you cannot validate them. So only the validated local models using this net are the ones to enter for this more updated of the global model. So in one phase we have the updated model that it's first sent to the ledger of the blockchain with the smart contract and with the last updated global models, and it's registered there and it's immutable. And in the other direction, this updated global model is distributed again in the net, so all the charging stations that set a local model can have the benefits. Also, this blockchain network allows us to let's say, adjust and benefit or do penalties to some of the charging station within this participation. So I'm going to start to be fast because I'm a little late. So digital twin. The digital twin. For in green, the digital twin is a virtual replica that we built to simulate the physical environment of a real city. We have placed different charging stations. Well, that's actually the real charging station in a city, and you can get the energy demand of each, but you can also adjust and have clusters. These clusters can be geographical, can be separated by fast and slow charging station or others. You can see the comparison. In closer detail, because you cannot see here because it's really far. But the reality is that what happening is this: we have different places charging station with the cars are moving and are charging when they need. We have some algorithms running there, so it's be the most realistic that we can do. So what allows us to have the digital twin? So it allows us to have a real time detailed up-to-date information. Also helps us to evaluate and react to different scenarios, because you can adjust the scenario, the initial conditions. Also, you can simulate different strategies, let's say replacing some charging station. You can form the new people into these newer scenarios. Also optimize the utilization of these assets or elements, and get also a statistical from the long-term analysis. So for the results, we start with two data sets. The first one is the Barcelona, and the second one was for US Colorado. So as you can see, they are a bit different. The one in Barcelona, it's only from 1 year, while the Colorado is for a few years. But the reality is that the one of Barcelona, even though it's fewer data, it was hourly, while the Colorado has some irregularizations. You can see also that in Barcelona there's a difference between the blue one and the orange one, and this is because the fast charging station and the slow that you can see better here. The fast are the ones in red that we have more data, and the ones in blue and also the green one, what is a special one, but are the slowest ones. What is important? Why is important? Differentiate between the fast and slow, because the fast ones, a fast charging station will charge around, let's say, 8 to 10 cars a day, while the slow maybe one or two. So they are in balanced state. So for the initial evaluation, you can see here the table and the first, let's say, not processed data of the dataset, and two different. The first one was the only with let's say a smoothing, and the results were really bad because it's really irregular. Let's say one Monday you can have three vehicles, but the next Monday you have 8, and there's no really a pattern to have here. So we need to have a pattern to kind of train the model, of course. So we adjust the data set to do the accumulate energy. Let's say you can see there's like a blocks. So each block it's 1 day. So we are calculated not the precision if in the hours, but the precision if in the charging energy accumulated in 1 day. This was the, let's say, the experiments with the traditional models, but the real results are here that a few of you can would see, because I presented them in the Frauel monthly, in the year summit. These are done with physics-enforced machine learning, and these models incorporate physical principles into the algorithm, so they can be better and more accurate to predict this energy time series. You can see that also the prediction is adjusted because it gets the new data that is getting from the instant zero, let's say. So these models are not only trained with the energy or historical energy or the consumption of the energy before, but also with different factors and different variables that we add, because the dynamic of the city is very variable. So it's kind of difficult to just only get good results with only the energy information. So these are a few, let's say, the size of the charging station, the geographical location, the month, the day, the climatology, the daylight price. Also, it can be important the price of the oil. So everything affects. So arriving to final, why we do this combination of technologies? Well, first, because the blockchain and smart contracts allow us to have security using this centralized structure, confidentiality, you can preserve the privacy using the cryptographic keys, immutability, because you have a permanent record that is almost impossible to alter, and encryption, you have the data securely stored using these cryptographic techniques. Here you can see the blockchain architecture that we use. I'm not going to spend some more time here, but you have 2 channels, one for the fast, one for the slow, northern. We have planned 3 companies here, and yeah, that will be big picture of all. Also, I'm not going to explain nothing new about fair learning, but you have the benefits of collaboration and having the distribution of the model training, but the only problem that we detect here, or the big problem we here, was having in a centralized environment. So what we have done is, with using this technology combination, the traditional structure will be centralized using a central authority and having to send all the data to the server. And with our new approach, we have a decentralized, the data and the validation process is done through the nodes of the network. So yeah, we can validate, and we can do few things that are really interesting in the area of the industry. So In the future, well, we have a few quick video of what are we doing in the interface. We have a map of the charging station, different APIs, and also the blockchain. If I'm gonna show you, yeah. Okay, so yeah, I'm gonna talk. I hope you can listen both. So yeah, here you have the map with the different charging stations. You can access to one of them, and you can have all the information here. To the right, you have the prediction of the next days, one of the next hours. Also, you can connect to different APIs. This is a sensor API. Also, this is the price of the energy, one of the Spain APIs, but you can connect to different ones. Let's say here you have the traffic information API. It's really interesting because if you are doing the geographical clusterization, it's important to know what is happening in every point, events, weather, traffic, and the sensors. So all these inputs are the ones that I explained before that are important for this prediction of the energy demand. And finally, we have the view of the blockchain that you can access for the channel policy or the information about the peer. Yeah. Okay, that was a video. And so, yeah, quick review. The applications with the combination of this technology helps with the decision making. Of course, because you have more information, helps to audit better. Also, you can have a prevention of the incident, and the time reduction will be with this expertise and all the project contributing to this urban sustainability. You finally have this time of reduction. Also, some of benefits more strategic that would be if a company make use of this platform, so have more operational efficiency, to have agility of the operation, a cost reduction because you can have some prevention. Of course, you have the effective resource allocation because you can know the available resources and where to distribute them, and also a constant availability of this thanks to the information. So green was not only a solution, it's a transformation that is using these three technologies, blockchain, federated learning, and smart contracts. This combination strengthens not only the operational efficiency, but also helps with the decision making. And we have also starting to do some other use cases. The big one that I will show you later, it's well now actually, is the one that about not only trying to predict the energy of the charging station, but also the big picture of the city. So the prediction of the energy consumption in a city. Also, we have some projects starting with using this technology for the logistics sector, the medical, and also for the mobility. In this case, is the ships and the vessels. So just to show you that this is not an invention, these are the results that we are having from the city energy prediction. As you can see, this one is about 24 hours. So we are predicting using only the 24 hours before and predicting the next 24 hours. But we, as you can see in the back part of the graph, we have done with a really big index of the window. The ones that is in the corner, this right corner, the bottom, is I think from 1 week. So yeah, we are getting really big nice results here. And just to show you that it's not an invention, we are using these technologies for other use cases, so it's really important. And to conclude, three key reflections. This Project Green and the collaboration of these technologies allows the collaboration, the immutability, and the privacy, and this is very important for the future development of the industry. So yeah, thank you so much. Thank you, Nick, for having me here. We are hope that maybe next year we are going to present in the Flowers Summit other project with this technology and more accurate to the further learning. You can send any questions. Well, we can ask now, but you can send any questions to our mails and access to the webpage. And also thank you to the team of the Green team that helps to develop this project and have spent a really long time doing this.
Great, thank you so much. It's pretty impressive system. Not only does it use a lot of machine learning and things, but it's obviously a quite a fully fleshed out system, being able to do all these predictions and connecting it with these energy charging sites and so on. Yeah, it's very cool. Well, if anyone wants to ask questions now, feel free to do so. I'll take a little look to see what we have, and particularly in the Slack, while people are thinking. But 1 second, let me see what I can find. Yeah, one question here is about just the question of blockchain, and if that component slows down the learning much, or does it kind of introduce new overheads that don't typically get seen? If so, how much?
So, okay, let's see if I can come back. Let me check. And I can show you also the better with the scale. Let's say maybe here. So yeah, we are not slowing down the process because if maybe here, well, we are just adding this decentralized structure in which we validate the models only. So the process will be kind of similar in terms of time, just a layer with the blockchain that has more benefits than other, because you have the let's say the authorized access with the cryptographic keys and also the security, and really important thing, the validation of the models, because you don't need to think as a one big blockchain network. It's more like I told before, but different channels where there are clusters where these charging stations work similar, so they can validate because the data that they manage, it's kind of similar in terms of geographical or in terms of fast and low. It's different. And also we are planning to start these adaptive clusters in which if we detect an anomaly, we can readjust the cluster in another channel of the blockchain.
I see. Okay, makes sense. Okay,
Yeah.
cool. Another question. Because it's just confirming that the results you were showing were driven by a mobility simulation, and they're asking if you also can use traces of actual observed mobility, like watching people, I guess, drive around in cars.
Okay, so yeah, we the results I have shown, they are not from the simulation. We have done the simulation in terms because we wanted to create synthetic data. We are to the conclusion that we already knew that it was kind of difficult, but it's possible to create synthetic data. In the beginning, we wanted to use only the synthetic data, but finally we arrived to these two data sets. As I told, there are kind of have difference, but the results are the combination of the data in the synthetic data of the simulation and the data of the datasets, specifically the dataset of Barcelona, because the simulation was also done using the Barcelona city. So yeah, these results that I have to do so fast, but yeah, the result was done using the both, but mainly the Barcelona dataset.
Oh, I see. Got you. I see. Got it.
Yeah.
Yeah. There's another question here. Let me just. It says, was the green deployment fully distributed via blockchain, or does it also have a server client model? And
Well,
what is the current and future scale of the number of edge clients? I guess it's a two-part question.
the second part, can you repeat, please?
What is the current and future scale of the number of edge clients?
Okay, so maybe I didn't explain that, but Green is a project in the TRL 4 to 6, so it's kind of a innovative project. So yeah, the sorry, I forgot the first one. Let's answer the second one.
Yeah. The first question is the green deployment, is it fully distributed via blockchain, or does the green deployment have a client server model as it runs?
Okay, so it's mix. Let's say here, maybe in the architecture, we are mixing. Let's say because you have different levels of mixing federal learning and blockchain. We are doing, as I told you before, we are finishing the project. So we are doing the last experiments in this because the models is closed. We are having really good parameters in the models, but we are doing some experiments trying to figure how mix we are going to have this interaction between federal learning and the blockchain network. So the architecture here is that the model is sent to the network to each node. We are working in, we have some options. First, having just not an authority, but some node that have a part of the prediction, of a part of the database or a similar, and can check this, can validate this model. And the other is that the ones that we are actually deploying, it's you send the model to a different as it was in the network policy, you in the blockchain policy, you set the model to the different nodes. Different nodes have to vote and validate through this algorithm, and then when you validate it, it's done. So it's we are working in these two parts. So yeah, we are still doing some innovation here, but the main objective is that in this month we close with this validation through this node. So I think we'll be fully mixed with all the blockchain. And the other one was that I stopped before. Green, it's not small, but between 4 and 6 TRL project. So it's an innovation project. So we have some things that still needs to manage that we are actually implementing more in the last the project that I sent. That is a big picture of the energy demand of a city, clustering by houses or clustering by streets or parts of the city. And in this project, we want to also add the ones that I told you, this adaptive cluster, but also some mechanism of differential privacy aggregation that I didn't mention here because the level of the project.
Cool, cool. We have one more question here, and that was it's a question that refers to some of the earlier slides you showed at the start, and they want to know what is the use case for space that you've been working on? I guess
Okay.
slide that shows some space. Yeah, I guess this one here. Yeah.
Yeah. Okay. So SEDA, it's a satellite data AI. It's a project that we are developing. It's started with Consciente. It's a program in Spain in 2018. We're actually developing the second phase of this project. You can, I think it's linked to the QR code, so you can check it. We are developing this second phase, and it's a project for the COBAM, and it's like the army of the Spanish army, and it's big. It helps to the defense analysts with the image satellite, with the image analysis of this vessel's information. So I don't know if you can see down here, but you have different tiles in a map, and you can have the information of we have a plenty variety of use cases like detection of vessels, also not only for the maritime environment, but also we're working with the land army. So yeah, we're working to detection of changes in the coast, changes in the terrain, new houses, new ports, detection of artillery. So yeah, we are working in different sectors. This is only a few of them, but yeah, if you check the web page of HI Iberia, you can see all the projects that we are developing.
Great. Yeah, very good. Cool. Well, then that's all the time we have for this talk. So thank you so much. This talk has been great. It was really interesting. Okay, yeah, and I just want to say, thank you so much to Madi, Sergio, Robert, who have really been the stars of this month. Speaking, they covered a lot of ground, very interesting pieces of applications and technologies and parts of Flower that hopefully the users out there will enjoy and to benefit from. And so I want to say thank you to them for spending their time with us. And thank you all for joining us for this month's update. Next month, Flower Monthly July, will be on the 3rd of the month, but the exact same time. So Wednesday, July the 3rd, come back and we'll have for you another interesting agenda of technical talks and updates for you all. So thank you all for joining us this month and take care. Thank you.